All right, well, happy Monday. It's week 7. Um, this is my slide deck, and it's just a big slide deck. We're going to use it today and on Friday. We'll see how far we get today. Hopefully halfway, and then we'll do the rest on Friday, and then you have the midterm exam on Wednesday. So I hope that's going well. The studying for that's going well. Okay. Well, anyway, let's take a look. The topic is support vector machines, which sounds so cool, right? It's like support vector machines, like ooh, but it's just drawing a line, okay? So that's all it is, okay? So it's a classification method, and basically you're just drawing a line between points on one side of the line and points on the other side, right? We're just trying to draw some kind of boundary between the two sides, and that's what we have. Okay, so support vector machines, it's a classification method. We're going to start with the simplest version of support vector machines, which is just what we call the maximum margin linear SVM, but again, it's just drawing a line, okay? And this method, drawing a line, is only going to work if your data can be separated by a single straight line, okay? And the idea is you find two parallel lines, okay? In 2 dimensions, it's a line, but you could also imagine this being expanded into higher dimensions, and then so in 3 dimensions you would be drawing a plane, and then in higher dimensions it would be hyperplanes, okay? And so you're basically just drawing like a small like train tracks, and you want your train tracks to be as wide as possible. All right, how can we do that? Okay, and that's it. Okay, that's the entirety of SVM in a nutshell. Is you're trying to draw some parallel. You're just trying to draw some train tracks, straight train tracks. You want them as wide as possible. Where can you do this? And then once you get that basic part down, then you can start messing around with some of the kind of this functional form of it, allowing it to have basically bends, and allowing it also to not be completely linearly separable. Okay, so we'll start off with this very simple case, and then we'll work our way up from there. Okay, so I'm going to start off with some points that are linearly separable, and so which one will be the one with the maximum margin? Okay, all right, so these I'm just showing a whole bunch of pictures to try to show you like where can we draw the widest train tracks. Okay, that's going to separate the red from the blue. Okay, and the blue are indicated with plus signs, and the red dots are indicated with minus signs. And where can we draw some train tracks? Okay, so we could try drawing a line just straight up and down like this, and so basically our train tracks are these dotted lines, and then I've got the boundary is going to be halfway in the middle of the train tracks. Okay, so I'm drawing these kind of just parallel lines, and this is one, right? But I can kind of rotate these, and then we can see we can get things that are wider, right? So that's pretty good. And this one's even better if you kind of run into these points, and then as soon as you start kind of going the other way, then whoops, they start getting thinner again. Okay, so this seems to be the widest, what we call the widest margin. Okay, the widest set of parallel lines that are as far apart. And therefore, if we take the midpoint, or not the midpoint, the line that's in the middle of these two, this is going to form our boundary. Okay, and this is what the maximum margin SVM would do. Now, again, technically, any of these would qualify as having 100% correct separation between what is red and what is blue. Okay, but this is going to be the best, and therefore everything over here will be blue, everything over here will be red. Okay, so how do we figure out that boundary? All right, so SVM says the best boundary is the one that's going to maximize that margin. The margin is defined as the perpendicular distance from the decision boundary to the closest points on either side, right? So when I draw these things, we've got kind of these closest points, and we have this decision boundary, and what is the perpendicular distance between basically these two sides? That's what we call the margin. And we want that to be as maximum as possible. And basically, the direction of this boundary, this location of this boundary, is going to be determined solely by those closest points. The closest points, these three, are what's going to determine this, okay? If I add more blue points over here or add more red points over here, the location of this boundary here is not going to change, okay? It's only if I insert a red point closer within inside this margin or a blue point within this margin or something, then that would change where the boundary exists. But if I add any blue points on this side of the margin or any red points on this side of the margin, the location is not affected. So because these are the 3 points that determine it, we call these the support vectors. So again, you can also think of points themselves as vectors, okay? Start, from the origin, you can have like a vector pointing at each of these things. These are the 3 vectors that determine this. These are known as the support vectors. Okay, and again, you can change the location of the other data points, and the location of the boundary is unaffected as long as those support vectors remain the support vectors, the closest points to the boundary. So we basically want to maximize this perpendicular distance between the parallel lines. This is our margin. We want to maximize that thing, okay? Versus if we had a non-optimal boundary, okay, this distance is much smaller, and so we would say this is not the optimal choice, okay? So mathematically, how do we go about this? All right, so we start off, we have our training data, and we basically have 2 classes. We either have a 1 or a -1 to indicate our classes, okay? So this is why I've got positive signs and negative signs. We're going to just say we've got, for a class, we've got +1 versus -1, okay? And the location is going to be x. So all of these, basically these points, x is going to be a vector, a d-dimensional, so in our case 2 dimensions, right? We've got the coordinates of the point, and then we have the label of a 1 or a -1. And what we want to do is we want to find the SVM, the line that divides the group of points with the labels +1 versus -1, so that the distance from the hyperplane to the nearest point, that is this distance, so this being the hyperplane, the distance to the nearest points is going to be as large as possible. Okay, and so when we do this, all right, the hyperplane is going to be written as the set of points x that satisfy w times x, w transpose x, minus b is equal to 0, okay, where w is the vector perpendicular to the hyperplane. Okay, so w is going to be kind of a vector that at least points in this direction here. And then we can say, all right, if we were to take the product of, w transpose x, x being this kind of all the points that lie along here, the cross product between any point along here and a vector that defines this is going to be 0, right? And then and so we have that, okay? All right, and then the parallel hyperplanes, okay, that is this dotted line over here and this dotted line over here can be described as, you know, W transpose X plus some constant B versus W transpose X minus some constant B. Okay. Or, I'm sorry, not minus some constant B. We got W transpose X minus B is equal to 1 is going to be that dotted line on this side, and then W transpose X minus B equal to -1 is going to equal this line over here. All right, and so we'll have x1 and x2 in kind of the next couple of pictures will be the closest points from each class, and they lie on the edges of the margin here. Let me go ahead and give you your first view quiz answer. The letter C. First one is C. Okay. C as in cat. Okay, so yeah, right here, maybe, let's see. So just so we have a sense of this, okay. This is tricky. Okay, so we need to have some kind of vector, right? We'll say this is our W vector, and just, okay, I guess this is not the case here, but let's just say this is the vector 1, 1, okay? And then to kind of indicate, all right, we want a line here, right? This is going to be a kind of our hyperplane, okay? What we're saying is we've got this vector, W transpose X. What do I have? Do I have plus B or minus B? Okay, just plus some constant, okay? Equal to 0. All right, so where do we have this, all right? So let's say this point right here, just for simplicity. Let's say, goodness, okay. So I could have points along this line, might include something like, okay, let's say this point is also 1, 1, okay? So we're going to take, if W is 1, 1, and we'll take this, having so much trouble here, okay? We'll do X is 1, 1 also, this point right here. We'll just let one of these things be 1, 1. All right, so W transpose X transpose will be 2, and we'll say B is equal to -2. All right, so what's the set of points, okay? The set of points X that are going to define this hyperplane, okay? We could have X equal to 0, 2, and if I do W transpose X, okay, minus or plus B, or B is equal to -2, what do I have? I'm going to have 1, 1. How do I matrix multiply 0, 2, okay, and this will equal -2, and we would see this is going to equal 0, right? And then I could also come to the point 2, 0. minus 2. This is also going to equal 0. And then even further along, this point right here would be 3, negative 1, right? So this would be, 3 minus 1 minus 2 is equal to 0. And so basically, all the points x that satisfy this equation will define this plane, this line, this hyperplane. Does that kind of make sense? Okay. And then if I said W transpose x plus b is equal to 1, that's going to give me a line that's parallel to this, right? So all x that satisfy W transpose x plus b equal to, actually, plus 1 is going to end up down here, I think, and minus 1, wait, I got to think about this for a second. So if I have 1 comma 1, and then I have, this will be like 3 comma 0, yeah, times 3 comma 0 minus 2, that will equal 1. Okay, so this point is going to be 3, 0, and then where would I be over here? This would be like 4 comma negative 1, right? And then we could see 1 comma 1 times 4 comma negative 1. So 4 minus 1 minus 2 is equal to 1, right? And then this will be, so this line over here is W transpose x plus b equal to 1. And over here I've got W transpose x plus b equal to minus 1. So these are forming hyperplanes that are parallel to the thing. Is that okay visually what's happening? How we're defining these things? So we're defining these planes, or these, in our case, lines, but in higher dimensions they'll be planes or hyperplanes, as the set of all points that satisfy this equation. W transpose x plus b equal to 1 will be this one up here. W transpose x plus b equal to minus 1 will be down here, and then the one that equals 0 is the one in the middle. So this is what I have, okay? And we're going to say we have some points along these hyperplanes that define these things, okay? And so we're going to look at these points and say these are the ones that are going to kind of max. We want to find the W such that we can maximize this distance here, okay? So if we just take the vector between, just let's say we pick 2 points, x1 and x2, which lie on these dotted lines, okay? What is this distance? Okay, so here we are going to project this vector onto this perpendicular line, right? So we take this margin in purple is the x1 minus x2 vector, right? So if we take the vector that defines the difference between these 2 points, we dot it or project it onto this vector w, which is perpendicular to the boundary. Is that also okay, right? The dot product of the vector is the distance in that direction. Okay, so we're going to say x1 and x2 are 2 points, and it could be, I could also have used this point and this point, right? So if I said we had this vector and we projected onto this, that would result in the same distance as well, okay? So x1 and x2 are going to be the closest points from the 2 classes. That vector x1 minus x2 joins the points x1 and x2. And with the way the boundary is defined, w is just a vector perpendicular to the boundary. And if we just want the direction, we can take w divided by the norm of w, and that will just kind of be a unit vector that's in that direction, okay? And so we'll say this distance is going to be 2 gamma, where gamma is basically the distance from the center to +1 or the center to -1. So you're going to say 2 gamma is equal to the length of the margin. And so if we take if we dot that vector x1 minus x2, or we can just basically do w over w norm, the direction, transpose x1 minus x2, we will say this is going to be equal to the length of the margin. So I want to make sure this is okay, the steps here. So we're saying this w over the norm w is basically a unit vector in this purple direction. And then we're going to basically take the dot product, or the projection of x1 minus x2 onto this, onto that direction. Okay, and that's what we have here. So we've got the unit vector dotted with x1 minus x2. Okay, or in our case, we could just do w transpose x1 minus x2. We're going to say this is equal to that distance. You know, here I've got 2 gamma. I'm just following the notation in the textbook, but you could just say it's some letter indicating the distance. Okay, and what we want to do is we want to maximize this distance. Okay, and so if we do a little bit of solving, okay, and we said, all right, well, let's, we're going to say w transpose x1 minus b is equal to 1, and w transpose x2 minus b is equal to minus 1, right? So we're saying we know the location of x1 is on that hyperplane, and we've defined that hyperplane, one of those to be the set of x points that satisfy the thing where it's equal to 1, and the other one's going to be the set of points that satisfy where it's equal to minus 1. So if I plug those things in, okay, so, you know, kind of just moving some things around, okay, so I could say, okay, if I've got w transpose x1 minus x2, I can kind of expand that out, w transpose x1 minus w transpose x2, all right? And here I'm allowed, I could subtract basically subtract b from over here and subtract b from over here, right? Because I'm subtracting a b and adding a b, and I'm not going to affect what's happening. And so if I do this, well, this thing, w transpose x1 minus b, we know this is equal to 1. And w transpose x2 minus b, we know this is equal to minus 1. So this thing just cancels out to just be 2. Okay? And so now I've got gamma equal to 1 over the norm of w. Okay? So this is the distance. We still want to maximize this thing. All right, is this okay where we're going so far? All right. So this is in the denominator, all right? And so basically, if we want to maximize the distance, now we're going to try to minimize, the norm of w. Okay, but we have some constraints, right? We have some constraints in that we can't just say, okay, well, let's make w as just tiny as possible, and then we're done, right? Because now we want to kind of just make sure that the constraints are that when we do w transpose x, okay, when we dot wx and we have minus b, that we're going to pick such a boundary so that for all the points that are in blue, that they'll all remain on that side of the boundary, and all the points over in red will remain on this side of the boundary. So we do have these constraints in that w transpose x minus b is going to be 1 or more than 1, greater than 1, for everything with a positive value, and w transpose x minus b is less than or equal to minus 1 for everything on the minus side, right? We need to make sure that if we did take these things are all going to be at least minus 1 or something more, and these ones are all going to be plus 1 or something more. Okay? And so one way to kind of summarize this, a clever way to kind of summarize all of this with just one constraint rather than having to worry about both of them, is that we could say, okay, the sign of this, where we have either 1 or minus 1, the label being 1 or minus 1, times w transpose x minus b is going to be greater than or equal to 1 for all of the points. Okay, let me give you your second view quiz answer, which is the letter D. D as in dog. D as in dog. Okay, so this is where we are. We have this constraint. We want to find the w, so where we can minimize the norm of w, but this has to be true for all the points x in our data set. Okay, so we're gonna have to kind of just make sure that for every single data point, this constraint is true. So we're going to try to minimize the norm of W, and the solution that minimizes this is also going to be the same solution that minimizes the norm squared, okay? And it's subject to this constraint, right? And so anytime you want to do a minimization thing subject to a constraint, we can use a Lagrange multiplier, right? And that's actually what's going on when we looked at ridge regression and lasso. The form of that thing was actually minimizing the OLS subject to some kind of constraint as well. Okay, but anyway, here, optimizing function subject to a constraint, we can achieve that using Lagrange multipliers, which is, what's that from? Is that 32A? 32B? Something around there? Something around there, maybe. Okay. Okay, so anyway, Lagrange multipliers, we add a new term to the objective function for each constraint so that the optimum of the new objective function corresponds to the optimum of the original constraint thing. All right, so anyway, we have the one constraint, and we're going to basically add this in there, right? But we have n of these things because we've got one for every single observation, right? Because every observation has to satisfy this constraint. So this ends up being kind of a big mess. In that, okay, so we're going to say, all right, we want to minimize this thing, and just to kind of simplify this, we're going to just do the norm squared. So we're going to have W transpose W here. That's the norm squared, and we still want to find the W that's going to minimize this, okay? But now it's subject to the constraint that we have T W transpose X minus B minus 1, right? So because we're saying this thing is basically we're adding that term, okay? And we've got a whole bunch of these things, right? We've got the Lagrange multiplier, and this has to be true for basically all of the observations that we have in our data set. Okay. So anyway, we get it in this form, and apparently all the resources I've kind of read get very hand wavy at this point. They say this is the problem. It can be solved using quadratic programming, and I don't know anything about quadratic programming, and I was like, well, maybe I'll try to learn about it, and then it was like too much of a headache. So, but apparently there's a way to get the answer numerically through quadratic programming, but there's not like a closed form solution. But I guess once you get it into this form, you can kind of put in these constraints, and then you can have the computer iteratively arrive at a place where you can minimize this thing, okay? And so when you do this, you get the solution for W that's going to solve this problem. Okay, and I know that's unsatisfying, and I was unsatisfied that we got to this point where the textbooks I read and a bunch of other sources just kind of say, okay, we got it into this form, which we can solve through quadratic programming, but I don't feel like explaining quadratic programming. And then I was like, if you're not going to explain it, who's going to explain it? And then, but apparently everyone just feels like quadratic programming is too hard to explain. So I apologize. That's where we are. Okay, but apparently we can figure out the direction of this. We get into a form where we can say we're going to minimize this subject to these constraints, and iteratively the computer can figure out how to minimize W subject to these constraints, right? And so basically we're at a point where we can add a whole bunch of things, and as long as we're not affecting the points that are closest or that lie on the boundary, okay, so like I hand drew some pluses here and I erased some of these things, the boundary's not going to change. It's only when you kind of mess with these things does this affect the boundary, okay? Now, um, that's where we go. Okay, so now these next couple slides are just a huge mess, but we can, yeah, we can solve the form that we solve via quadratic programming is a little bit requires a little I guess additional work here. All right, so if we want to minimize this, we're gonna take the derivative of this with respect to w, and we set this thing equal to 0. Okay, at the minimum, the derivatives of this function with respect to w and b will be equal to 0. So when we take the derivative of this, okay, so w transpose w, 1/2 of that will become w. And then if you kind of expand all of this out, and you take the derivative of this with respect to w, you're going to get the sum of alpha, t, and x, okay, for every n observations. Okay, and then we set that equal to 0, and therefore you're going to get w equal to the sum of these things, right? So we get the sum of alpha times t times x. Okay, so this is kind of an interesting form here, and we'll talk about this in a moment. If I take the derivative of this whole thing with respect to b, okay, well, this is going to zero out, okay, and basically a times t, this part zeroes out. I've got a times t times b, and then the derivative of that with respect to b just becomes alpha times t. The negative sum of that, we set that equal to 0. And so, don't worry, okay? This is like the craziest slide, and my eyes were like bleeding trying to make sure I got all of these subscripts correct, okay? And I think I got them correct, but I might have made a typo somewhere, and it's so hard to catch your own typos when you have all these subscripts. But anyway, we're going to take this form here, okay? Which basically all this is saying is w is equal to the sum of the x vectors, all right? Except the term alpha here might be 0, it might be 1, it might be something in between. In our case, it's going to be 0 for everything that is not the support vector, and alpha is equal to 1 for the ones that are, for the 3 that are on the support vector, alpha is equal to 1, okay? And then for everything else, alpha is equal to 0. That's effectively what's going to happen when we solve this thing, okay? And that is why this w is not affected by the addition or subtraction of x points out here, because the alphas, when we end up minimizing these, the alphas for those terms end up being 0, and the alphas for these ones end up being 0. It's just these 3 that determine the w, the alphas are equal to 1. Okay, and for everything else, it's 0. So anyway, this is what we have. We're going to we plug in this solution that w is equal to the sum of alpha times t times x. Okay, and we put that into here, and we put that into here, and to kind of to do the sum product of these things, we have to take. We change up the subscripts from m going from 1 to n, and n going from 1 to n. And what this basically means is if you have like 5 points, you have to consider when m is equal to 1 and n is equal to 1, when m is equal to 1 and n is equal to 2, when m is equal to 1 and n equal to 3, and then you do all 5 for that, and then you go to m equal to 2, and then so basically you have a total of like big N squared, so you have like 25 of these kind of combinations, and that's just for 5 points. And if you have 20 points, you have 400 of these things. So it's a huge mess, okay? So we have that. Something similar also going on here when you have the sum of from n to 1, n equal to 1 to n. Over here you have the subscript n and the subscript m over here. And so considering all of these things here, and so now you have all of these things, a sub m, t sub m, x sub m, and a sub n, t sub n, and x sub n, and oh gosh, it's a tragedy over here. But apparently, some of these terms cancel out. Where did they go? Okay, so basically this thing and these things can combine. I've got a plus 1/2 this whole mess minus a 1/2 of this whole mess. Okay, and so then we're gonna get minus 1/2 of the whole mess. Okay, and then over here, this we keep this thing and what did I do? Somehow I said this zeroes out. I'm trying to remember. Oh, wait. The sum of the a's times the... Something zeroes out here. I can't remember. Oh, dear. All right. Yes, thank you. Okay. Yes, when we do this thing, we said this thing is equal to 0. Yes, thank you. You know, eyes bleeding again. All right, so we got this thing, and then again, because at the solution here, we set this equal to 0. So this thing equals 0. Yes, thank you. That's what's going on. These two things combine, so now we have the sum of the alphas is equal to minus 1/2 of all of this, all right? And again, this is what we're trying to do, okay? And so we want to find the optimum of this subject now to the constraints that all of these have to, every alpha has to be greater than 0, and the sum of all of these things is going to equal to 0. Again, we say at this point, this is apparently the easier thing that we can plug into the computer, and we find this via quadratic programming. The solution actually doesn't contain any reference to W itself, and it's going to be basically we look at the x terms inside the that form the support vectors. Okay, so we have this the solution W is expressed as this, and basically the values that are not support vectors will have alpha equal to 0, and the ones that do influence will have a value of alpha not equal to 0. Okay, and I guess they're not always going to equal 1. It's going to equal to how much weight they get calculated. So it's a matter of figuring out which points have alpha equal to 1 or not, or alpha equal to 0 versus something else as far as which points influence the direction of W. So that determines these things, and this is what we call the hard margin, in that none of the points can end up being on the wrong side of this. So the optimization problem, despite as crazy as all of this appears, it's a matter of figuring out which points influence the affect the margin, that boundary. And so what we can do is we can ease up our restrictions by using what's called a soft margin, okay? And so when we did the maximum margin classifier, this was the constraint. We said everything has to be on the correct side of the boundary, and when we had the location of the boundary, everything had to be farther away. We can say, instead of saying the boundary has to be 1 or not, we can allow it to be, we can allow some of the points to be closer to the boundary than 1 itself, okay? So we can have, rather than saying it has to be 1 or more, it can be something a little bit less than 1, okay? Where we have some, I think this is xi, okay? This symbol is the Greek letter xi. I don't even know how you would write this by hand, but this is what appears in the textbook. how do we write Greek letters by hand? It's like one of those things where it's like, I don't even know, right? It's just some squiggle, and you have to say, well, this is xi, this is xi, okay? And so basically, we're gonna say, we pick some boundary w, so that w times x minus b, okay, is gonna be, greater than or equal to 1 for a lot of the points, but for some of the points, maybe it's less than 1, and for some of the points, it actually could end up being on the wrong side of the boundary. Okay, so this seems very strange. All right, and so the idea here, where did my thing go? Okay. So if I have okay, so let's have some red points here. So kind of the maximum margin classifier, I think, would probably end up forming a boundary that looks like this. Okay, it would be on this point right here. Okay, this would be kind of the maximum margin classifier. Now, what if we had a point, like right here? Oops. Oh, gosh. Okay, so if I put a point right there, where would my maximum margin classifier end up being? If we said, so with a point right there, the new boundary would have to look something like, this is, oh gosh, it's so hard drawing a straight line. Okay, oh, look at that. All right, I have a straight line tool. Oh no, now it's too straight. Okay, it would kind of pass through that thing, and then we would end up getting some kind of margin here, versus all of the other points being, I don't even know if this picture is even making any sense here, versus the original without this one dot here, this being kind of our culprit here. This one dot forces the entire margin to end up over here, because otherwise, with the boundary, right, with the maximum margin classifier and the center line being like right here, this dot would end up on the wrong side, right? So let me see if I can delete all of these lines. Okay, I can't. What we're gonna say is, you know what, let's kind of keep this. Sorry. Okay. It's like, can we still keep this boundary here? And then if we say this is, we look at this vector that's perpendicular to this line, right? So if we kind of keep this thing, and we say, okay, W transpose X, and we include this one, okay? So this one is going to be W transpose X plus B is equal to 1. This one over here is W transpose X plus B is equal to minus 1, okay? And this one over here is going to end up being something like W transpose X plus B is equal to, say, what, 0.8 or something. It's not quite on the boundary, but it's on the wrong side, all right? And because of its label, this label is on the negative side. T sub n is equal to -1. So now we've got T sub n times W transpose X plus B is going to equal something like -0.8. All right, so now we've got kind of the wrong value here, right? In that T times W transpose X minus B is not greater than 1, but it ends up being 1 minus 1.8 or something, okay? It ends up being on the wrong side of the boundary. So this allows for, by including this thing, okay, it allows for things to end up within the margin or even on the wrong side of the boundary. So our optimization problem now is going to be equal to this, and what's happening here is that we're putting an upper limit to what alpha can be. Okay, so when we're calculating the values of alpha, let's say these are the points that end up determining the boundary. Okay, so the W's times the alpha times your X's. Okay, we're putting an upper limit on alpha in that there are limits to how much a single point can have on defining the boundary. So over here, when determining the direction of the boundary, we would end up to be putting some kind of alpha value on this point, indicating it's going to have a strong influence on where the boundary is defined. When we have the soft margin, we're putting on a limit to saying, this point can influence the boundary, but we don't want it to have so much influence that it's going to kind of just change the entire direction of that boundary location. Okay, so we're putting upper bounds on how much any one point can influence defining the boundary. It's a little bit, right now we're kind of in these, it's just a whole bunch of symbols and it doesn't feel very concrete yet, okay? On Friday, I hope to kind of, there's a whole bunch of pictures that hopefully make it a little bit more clear as to what's happening when we put in these different values and parameters for how these margins are defined. Okay, so we'll put it on pause here. We'll put the lecture on pause here. We'll pick up on Friday to continue talking about support vector machines, and hopefully with some pictures, it'll make a little bit more practical sense what we mean by changing these parameter values and seeing how much influence any one point can have on defining the boundary and things like that. So we'll do that on Friday. But on Wednesday, you guys have your exam. And so good luck as you study. We'll see you then. I'll send out a seating chart, and we'll see you guys on Wednesday. Oh, third view quiz answer. Thank you for that reminder. It is the letter A. A as in apple. A as in apple. Okay, we'll end there. Have a good rest of your day. See you on Wednesday, and good luck.